Yes, thank you very much. Hi, and welcome back from lunch. This is always a great spot to present at after lunch. So just for your information, this is going to be a pretty technical talk. If you feel like you need to close your eyes to understand better what I'm talking about, you're absolutely welcome to do that. And kudos for coming to my talk because the chairs are much more comfortable in the other places. So thanks for it. All right. So my name is Geri. I work for Fortinet's FortiGuard Labs. I'm originally from Hungary. I live in Germany. And I come with an ethical hacking background. I was doing penetration testing and offensive security research for a long time. A few years ago, I changed to the other side, and now I do more threat intel and malware research. And this is also what I'm going to talk about now. Quick agenda. I will do some introduction to general topic and control flow flattening. And then we are basically going to talk about 3 different ways to deal with control flow flattening, which is going to be pattern matching, emulation, and symbolic execution. So that's kind of the rest of the talk. All right, so intro. A little bit of background, why we are talking about this, or why obfuscation and control flow flattening is getting more and more interesting to deal with, is because of how the cybercrime industry, let's say, or business has changed in the past 10 years. So, in the past, if you were a cyber criminal, you would do the whole kill chain. You would do your reconnaissance, you get initial access, you would deploy your malware or whatever, steal the data, etc., and win the money. Now this changed a lot since then, and the main thing that happened is that different groups started to focus on different parts of the attack and basically doing only that, and then ignoring the rest. For instance, initial access brokers, they basically get access to organizations, and then they sell that access, and they don't care about how actually it's going to be exploited. Or malware as a service, ransomware as a service providers, they focus on building their service, creating better malware. And in ransomware, they maybe do ransom negotiation as well, but they don't care about the rest. They are not actually going to carry out the attack. Now, good thing for people trying to enter the cybercrime market is that they can do it easily because they can just buy the initial access from somewhere, then they can buy the malware for somebody else, and then they can just go in with the initial access or the passwords or whatever, and then deploy the malware that they brought, and then everybody kind of wins, except the victim. A side effect of this is that I mentioned that malware authors now, wants to build, better malware, not just for fun, but not just because they can, but they also are competing against each other. So whoever writes the best malware, they're gonna make the most money. And one way to build a better malware is to make it more difficult to analyze. So obviously, obfuscation, anti-analysis, anti-reverse engineering techniques are really important for them because that's how they can compete against all the other malware authors. To underline this, a lot of talking with a little bit of data. This was from FortiEDR. It's just a statistic of half a years of detections, and what it shows us that EDR detects, a lot of defense evasion techniques. So that's the majority of detections. So that kind of shows us that this is really happening. As I didn't make it up myself. And why using obfuscation? So, obfuscation is not rocket science. It's not a silver bullet against all analysis. It's more like a ball and chain. So, instead of making analysis impossible, it's just going to make it really painful for the reverse engineer. Obviously, there are different obfuscation techniques. There are different levels of possible obfuscations. We are going to focus on control flow flattening in this talk. There are off-the-shelf tools, most of them open source, for basically all programming languages that you want to use. Again, we're going to focus on C here, just because that's what I'd like to use. But we could take any other language and do the same exercises on those as well. All right. So now let's get into control flow flattening. So you probably already figured control flow flattening is an obfuscation method. It's, as all the other methods, it's very cheap for developers. So basically, control flow flattening your program takes like 3 seconds after you set up the environment. But it can slow analysis down extremely, especially if it's combined with other kinds of obfuscation techniques, which I've also seen in the past, in different malware. The main idea is what you see here on the. Oh, actually, I have a clicker. I totally forgot. Yeah, the main idea is what you see here. This is actually from Tigress. We're going to talk about Tigress a little bit later. It's an obfuscation tool, and this kind of shows us what's happening here. This is a control flow graph of a function. So this is one function doing something. And the good thing in control flow graphs, so if you're doing reverse engineering, then the point is that you're just looking at the control flow graph, and without knowing anything about the function, like in 2 seconds, you already learn a lot. So if we take this example, we see things like, there is like a loop here, and then, 2 different things can happen in the loop. So there is some kind of if here that decides what should this iteration of the loop be doing. And here is some kind of condition that decides whether to exit the loop or not. So this is a very simple function, and we already learned a lot about it. So, if we want to figure out, the core logic of the function, we know where to look. Maybe these here, or maybe the, exit conditions, and then we have like 80% understanding of what this function does. And what control flow flattening does is turns this control flow graph in this one. So it doesn't really change the actual business logic of the code. So it's going to do the same thing, just the control flow function is going to look differently. The most basic way to do it is to implement like a state machine, and that's what we see here. So we have like different states, and there is a dispatcher, and then after each block was executed, or this state was executed, it's going to return to it's going to set the next state, and then it's going to return to the dispatcher, and then based on the next state value or algorithm, it's going to decide which state execute next. That's also why it's called flattening, because it's going to create these flat architectures. Just to start to talk about naming conventions, I call original basic blocks these here, which are basically implementing the original code of the function. And then we have the dispatcher. That's just the logic that decides which original basic block should be executed next. And if we look at the real function from IDA, then again, here you see this is again still a relatively simple function. There are a couple of ifs, I think 2 loops in it, but ultimately it's not a lot of code. And if we do like the simplest control flow flattening that we can, we get this one. So this looks already much worse. So it's, and this is again for a very simple function. And what you see here is that, I used Tigress for this. Tigress is a source code level obfuscator. So basically, you give source code to Tigress, and then it's going to output a new source code with flattening or other obfuscation implemented. And what you see here, we have basically an endless loop, and then we have a huge switch case in it, which is basically the state machine. I already talked about it. And then here we already see that that V11 is the state value, and basically every block is going to set V11 to some new value, and that's going to tell the dispatcher which next state should be executed next. And this just represents my, emotions while I was reverse engineering a control flow flattened binary. This was in .NET, that's why it looks even worse than it should be. But once you look at like a control flow graph like this, you don't really want to look at it anymore. So it's like the initial reaction is not to reverse engineer it. And I guess that's the whole point of the obfuscation. To do all these exercises and to test the different techniques I'm going to introduce, I obviously wrote my own malware. As any modern hip developer would do, I use ChatGPT to do that, and I use the state-of-the-art 1-byte XOR for the actual encryption. It's gonna just change the so it encrypts files. It looks for files on disk based on extension list. It encrypts the files with the 1-byte XOR, adds .noob extension, and removes the original file. What you see here is the encode and save files function. This is what we will use in the following exercises. So that's why I put it here. It's very simple. This is the part where it does the actual encryption and renaming of the file. And Tigress. So it comes from academia, but it got very popular. It's open source. I kind of already explained the rest. So this is basically the one line that you have to do to obfuscate your original source code. We apply the obfuscation per function. So in this case, I told it to only obfuscate this encode and save files function, and this is basically the obfuscated version of the same function that we've seen before. Obviously, it's gonna be much longer, but otherwise here you again see the same while and the switch case. Then here it's pretty obvious that this is going to be the state variable, but often it's not so obvious. So we're going to counter control flow flattening somehow. So that's kind of the whole point. So how to do that? As I said, this is pretty much my initial reaction. So that's what our instincts tell us. But obviously we have a job to do, so we need to figure something out. There are different ways to do it. In this presentation, I'm going to focus on the static version. What we want to do is to restore the control flow somehow. So, the biggest annoyance in control flow flattening is that like you don't see the whole structure, you don't know where to look in the code, you don't know which basic block is going to come next. So you just don't have this information, and it's really, really difficult to do static analysis. So the main goal there is to restore the control flow somehow in a way that you can comprehend it. And for that, I mentioned I will use emulation, symbolic execution, and pattern matching. But we can also do it dynamically, and especially if you're under time pressure, then I would suggest to go for dynamic analysis first, because all the others are not really quick works or jobs. But dynamic analysis can give you useful information faster. So, for instance, if you do like a couple of sandbox detonations, whether on commercial sandbox or your own VM, then you can extract IOCs quickly. That if it's part of incident response, then maybe that's what you need to kind of move forward with the incident response, or enrich the threat intelligence you already have. Debugging can be really useful. It's a pain because you basically have to, click through the whole function to understand what it does. But at least you're going to see, whenever it calls some kind of Windows API or something like that, you're going to at those points you're gonna understand what's happening. So dynamic analysis is a very good alternative, but it doesn't give you the full picture. But here we're going to focus on static analysis. So restoring control flow. This is kind of the main, process of how we want to do that. First, we want to identify the original basic blocks. I mark them here with green. Usually by looking at it, it's really easy because those are going to be the longer blocks and those that are here in the middle. Because they're going to be the longer blocks because they are the blocks that actually have some kind of useful logic, not just the coordinating the obfuscation. Then we want to identify decision basic blocks, which are marked here as blue, because what's happening is that if in the original code you have a basic block that ends in a branching, so like a true-false branches. Then in the control flow flattened version, these two things has to be separated because of how the dispatcher works. So there, as you can see, none of the original basic block has a branch at the end. So all of them returns here at this block, which is going to return it back to the dispatcher code. So whatever the original basic block had a branching at the end, then it's going to move into a separate decision basic block with two new, where the decision is made, which branch to take. And then the white blocks basically just set the state variable according to which next state should come or which next block should be executed. So when there is branching involved, then first an original basic block is executed, then it returns to the dispatcher, it goes around, goes to the branching block, it makes the decision, sets the next state variable, and then returns to the dispatcher and goes back, and that's how it's going to go to the next original basic block. So there's like a two loops of dispatching here. So if we identify original basic blocks, the decision basic blocks, we identify the state variable. Usually it's pretty easy because at the end we need to set the state variable there, and then this logic also uses state variable to make decisions. So by looking at the assembly code, it's not really difficult to do that. Then we map state values to original basic blocks. So we need to know this original basic block is state value 1 or 2, or however the state is managed, but we somehow need to map the two together. Then we need to recover which next states should come after an original basic block. It could be either 1 or 2, depending whether the original code had branching or not. So for instance, if this guy runs, we need to figure out which original basic blocks should come after that. And if we have all this information at hand, then at that point we can reconstruct the original control flow just by putting all this information together. All right, let's go into the first technique, pattern matching. So I don't know how is it in your country. When I was 17 and I did the driver's license exam, obviously when we sit in the car, every time we have to check the tire pressure and the brakes. So, and I've been told by my instructor that on the exam, before I sit in the car, I just look at the tires and I say that with visual inspection, I determine that the tire pressure is adequate. And with that, we're basically done with that part of the exam. So that's kind of how pattern matching feels, because we are just looking at the code and then trying to put together some kind of heuristics to decide which basic block this is. So, pattern matching, static analysis only. We're trying to establish patterns in the assembly code to figure out how to identify the different kinds of basic blocks. So, for instance, if we look at an original basic block like this one here, then the heuristics could be that it has more than 3 instructions, because as I said, it has to run some kind of logic that is useful. It has a last instruction as a fixed jump because if you remember the previous slides, all of the original basic blocks go into the same basic block to return into the dispatcher. So the fixed jump is always the same. And the second to last instruction is a move something, because that's where we set the state variable. So in this case, our state variable is stored here, and this is going to be the value of the next state after this basic block. So this is the heuristics I put together for this for identifying original basic blocks in this specific case. And this is pretty much how we implemented with Python. Obviously this is it very depends on the malware, and that's kind of the disadvantage of pattern matching, that your script is gonna work only for that specific malware that you created it for. On the other hand, it's pretty simple, and you can easily implement these things in Python / IDA-Python. All right, so a reminder that I should do a demo here. So I will try to do a live demo, but you know how that goes usually. So I have, yeah, exactly. This is how it goes. Yes. Okay, so we have this is our encode and save function that we've seen previously, and yeah, that's where pattern matching. I think that's where we are. Yeah, so this is basically the script. You can see that in this case, it's like 180 lines to decode this particular function, and we can look at the code a little bit because we have, I think, plenty of time. Yeah. So basically what we do here is the most important part is find blocks. So, I just showed the example of the original basic block, but I implemented similar heuristics for decision basic blocks. And this is basically, it goes through this if. We are, iterating through all the basic blocks, and then we are trying to decide which of them is original basic block and which of them is a decision basic block. For instance, you can see here that it's a decision basic block if it's short, and then we have some kind of compare in it, and the last instruction is some kind of conditional jump. And then we look into the next, or we record the two directions, the true and false branches for this. And then we basically, build up a database using this logic, and then at the end we just have to visualize that database. Okay, so no. Sorry, it's. Yeah, let's do it this way. So it was pretty fast. As you can see, here are just a few logs. It detects some original basic blocks, and it detects some decision basic blocks. And this is basically what we wanted at the end. We create a graph that looks like this, but in a second I show you in a more useful way. So this is basically what we saw there at the end. This is the graph that was generated, and and if we visualize it, this is how it looks like. Now we can play around a little bit of how these nodes are organized, but I can tell you that it's the same as the original control flow of the binary, or of this particular function. Now I experimented a lot with trying to restore this in IDA Pro. So basically try to make it look like this in IDA Pro from the script. My kind of conclusion was that it doesn't worth it. So Because you can make these different connections in IDAPRO, or you could patch it in the binary itself and then reload it in IDAPRO. So there are like different ways how you could try to restore the actual control flow in IDAPRO, which is, if there is no other obfuscation, it might work in a decent time frame. But if there are other obfuscations implemented, then it's probably not going to work in a decent time frame. So ultimately, what I decided is just it's easier to create this control flow for yourself, which you can have on the side, and then do the analysis still in IDAPRO in the obfuscated control flow, and then just when you want to know where you're at, then you just look here and see which block is executed next, and then you do have the information, but it's just not that easily accessible. But I think it's, in terms of time, it's not worth to go into rewriting it in IDAPRO. All right, so that's it about pattern matching. Now the next thing is emulation, and for that I use Flare-Emu, which is an emulation framework from the Flare team, which I don't know whether it's not FireEye anymore, maybe Mandiant, maybe Google, I don't know. But Flare is great. So look at Flare-Emu. It's a really great tool. I also tried to use. So here I say I use it for low-hanging fruits, which with that I basically want to say that. What I'm doing is instead of trying to reconstruct the whole control flow, I will just let it run, let it emulate, and see how good the results are. I tried in different cases to use emulation to reconstruct the whole control flow, but again, from a time perspective, it again doesn't really worth it. So because it's emulation. Obviously, if the function makes other function calls or API calls or whatnot, the emulator emulates it to some degree, but it's not always great. And then if you really want to put together a whole control flow, you have to force the emulator into going into all the different paths. So that's really a pain. So my recommendation is really just use emulation as like finding low-hanging fruits. You will see it in a second what I mean with that. I still use pattern matching to identify original basic blocks because it's just much simpler than trying to force emulation on that. Interesting part on this is that for emulation I had to create arguments for the function call to make it run decently. Obviously, these arguments can be total fake. So, for instance, I referenced the test2.txt file, but there is actually no test2.txt file. But because it's emulation, it's not even going to look at the file system at all. And to look at the code a little bit, so we basically instantiate the emulator. And then we call this emulate range and tell it to emulate this particular function. So we are just emulating this one function. We are setting an instruction hook. The instruction hook is a function in our code that's going to be called. So it's a callback function that's going to be called every time a new instruction is found. So basically, we run this function before the emulation of each new instruction in the code. So that's how we can record what's happening and we can, do different things. I set the function arguments here. The user data is just a way to preserve data between emulation blocks. So we can put anything there, and then that's what we can use before or after the whole emulation thing in our own program. So this is the instruction hook. The logic is very, very simple. So because in this case, we are actually just tracing. So we are not doing any kind of magic. We are just emulating the function and recording which basic blocks were executed. The only reason that it's more than basically 3 lines is because I put there like a instruction counter, and then like a maximum executed instructions. just because if something goes wrong, it would just run forever, and I want to exit after like 10,000 instruction calls, which you see here at the bottom, because then something obviously went wrong if we are at that point. But otherwise, we are just recording the executed basic blocks in a structure. All right, so let's do another demo. Emulation. So here you can see this is even shorter than the pattern matching we had. It's like 150 lines, including my very, very useful comments. Yeah, and then let's run it. And it runs a little bit more because obviously it's emulation. And as you can see here, I also built in a couple of like statistics, so coverage of that, basically how many of the basic blocks were executed compared to all basic blocks in the function. Similarly, original basic block coverage, how many of them were actually emulated compared to all of them. Now, as you see, the coverage is not so great, which kind of made me sad at the beginning, because it's like 50% coverage for basic blocks and like 40% or something for original basic blocks. So it's not great. So I thought this didn't work at all. And also, once I visualized the result, which is like this graph, it's super simple. So I was like, then emulation didn't really work. But once I actually started to look into what code is in these basic blocks that were executed, then it turned out that it was actually very useful. So I just put some notes here. So the first basic block is starting the function and logging to the console. Then the next one is opening a file. Then we read the content of the file. Then we are encrypting the content of the file. So what it turned out is that this is basically what this function does. So apparently all the rest of the function is more or less error handling and exception handling and whatnot. So and that's why emulation can be very useful, because if you can tweak it in a way that it's going to actually execute the part of the code that you were interested in, then it gives you results really, really quickly. Because ultimately our whole point is to figure out what basic blocks we should reverse engineer in more detail. So what we should look at. This tells us that, we should look at these 4 basic blocks, because that's where the most important part of this function is located, and when we can ignore the rest. So in these terms, this result is actually better than the previous one, although we don't get the full picture, but we get the added value of knowing which basic blocks we should reverse engineer. All right. And now, finally, symbolic execution. So this is kind of how I feel when I do symbolic execution. It's a selfie. And I'm dealing with symbolic execution since a long time. I was in different projects in my previous job, and then so I played around with it a lot, but it still feels like some kind of dark magic. And in some way, it's really like that. So when we talk symbolic execution, it's basically executing the binary with symbolic values instead of fixed values. So instead of having like a fixed file name that this function gets, it's just a symbolic value which represents all possible file names. And the symbolic execution engine runs every execution path at the same time. Now, from this, you can figure out that the problem with symbolic execution is that it really quickly goes to path explosion. So, because it runs all the paths at the same time. So that's where concurrent execution comes in, where we try to concretize values in the execution in a way that it focuses only on that part of the code that we are actually interested in. So, like if you play capture the flags, symbolic execution is what you want to use when, like, if there is like a serial code generator and there is a string says, valid serial code, then you want to do symbolic execution that leads to that point when it says valid code. And then with an SMT solver, it's going to tell you it's going to give you one serial code that was valid. So that's kind of how you can use this. So this is the logic that we are going to try to use it here as well, to figure out different parts of the steps that we did in the past. So one thing we want to figure out is, the mapping of state values to original basic blocks. There we would just say, like, execute symbolically till the beginning of all original basic blocks, and then we just look at what's the state value at that point. That's how we recover the state value for each original basic block. And that's what we'll see here. So we are just say, we are setting up the execution, and the original basic blocks we have from the same code as we use in pattern matching. And then we say, okay, for each original basic blocks, run a simulation till you get to that address. And then if there is an active state, so if it was actually possible to navigate to that point, then we just recover the value in this. Oh, sorry, I'm showing on my screen. So this is for each original basic block, emulate until that point. That's explore. And then if there is an active state there, then you can look at this memory address where the state value should be and concretize that address. Because at that point, that's just a mathematical formula that tells us what the conditions of a valid state value there. But if we concretize this, we are going to get one specific concrete value. So that's how we get the state value for each original basic blocks. Now, we can do the same thing for recovering the next state, where we says, okay, let's just single step through the code till we reach another original basic block. So, and then once we have that, then we know that that's going to be a next state. And the only thing we have to pay attention to is that there can be either one or two next states or next original basic blocks, depending on whether there was branching involved. And that's also pretty easy. We're just setting it up here, and then we do a while. Also, there is some protection here that we shouldn't go more than 20 steps because the next original basic block shouldn't be that far. And then we are just doing single stepping. And then at each step, we are checking a couple of things, mostly whether we reached another original basic blocks. If so, then we found the next original basic blocks. And then we also checked whether there are one or two. Yeah, this is where we check whether we have one or two next states. So if there are two active states, then we have to continue this until we find both. If we have only one active next step or active state, a state here is the symbolic execution engine state. Then we can quit, and then we have the next original basic block already. And let's do the demo again. And this is symbolic execution. So again, this is also pretty short. And it's running. So Anger, the symbolic execution engine, likes to talk a lot. This is the part where it's risky that it's going to run forever. Yeah. I was worried here a little bit. So ultimately, we got, again, a graph after all these computing that we did. And this is what we got. And, you can already see it's very similar to the other one we've seen. There's actually one difference is that one basic block is missing, but it's because of the a missing error handling or exit basic block. But it's not really important for the logic. Obviously, you can tweak it a little bit to show that as well, but I didn't want to because it seemed very unimportant. Now, let's give an honorary mention to debugging, because actually, when I first started to look at the control for flattening, it was a ransomware, and I tried to do some kind of smart things that I showed you, but it didn't work. There was also like multiple layers of obfuscation on it, which kind of killed all my attempts to make something useful. So, at the end, I just sat down and did the dirty work and, single step through the application multiple times. And it worked. I mean, I figured out what's happening, where it does it, etc. I didn't get the full picture of how the functions are looking, but ultimately, in terms of functionality, what the ransomware did and how it did it, I could recover with debugging. So, debugging can be really useful if you, ultimately, doing the same thing using symbolic execution can take more time than actually single stepping through the application. It really depends on, how versed you are in doing symbolic execution. So, to draw some conclusions, control for flattening is hell, and if you see it, it's going to be painful. As I said, especially if there are like additional layers of obfuscation, then it's going to be even more painful. But if you want to deal with it somehow, these are my recommendations. So first try, sandbox execution, running it on your own malware to collect different IOCs, get like a general idea of what it does. And often, you will see where it writes files. If it's just a downloader or a dropper, then you can recover the next payload, and then you can continue your work, so you don't have to waste so much time on that thing, which is not necessarily so important. So once you've done that, then I would say try emulation, because once you used Flare-Emu a few times, then it's not so complex anymore, and then you can do it in an hour to set it up and run the emulation, and then for the first function, and then for all the rest of the functions, it's going to be more or less the same thing. And if it brings you good results, like the one I showed you, that's great. Then you won, and then keep doing that. If it doesn't give you good results, or it kind of fails doing a good emulation, then I would say let's go for pattern matching. See whether you can build heuristics relatively fast, and whether you can implement it quickly. And if time allows, then go into symbolic execution, just because of the complexity of the technology itself. If you already know symbolic execution really well, then maybe it's going to be faster for you. But if you don't, then probably it's not going to work as part of an incident response or anything like that. All right. So thanks very much. I was Geri, and thanks. Are there any questions?
First of all, thanks for the tips for tomorrow night and the checklist. During my studies, I had few courses about branchless programming, which is the opposite of flattening, I guess. Is it something that you encounter as an obfuscation technique?
Yes and no. So, for instance, control for flattening can be implemented also various ways. Like if you just go to Tigress, it implements like 5 different ways of doing control for flattening. So what I showed is the simplest way, the state machine way. But it can also do like basically move every original basic block into a new function and things like that. So so there are multiple ways to deal with this. I don't see that though a lot. So mostly when I see control flattening, I see this one. That's kind of why I talked about this. But yeah, it's possible.
Okay, thank you.
Sure.
Hi, thanks a lot for the talk. It was really interesting to me because I was actually implementing control flow flattening at my job.
Oh, cool.
So I wonder if
Thanks for that.
I wonder if you could give us any tips to make it better. Anything that would make your job a lot harder. Any of these automatic.
Well, let me think about that. No, so yeah, to be honest, like the one I mentioned, for instance, where I was debugging a lot, there they had like obfuscating jump addresses as well, and obfuscating call addresses, and then the combination, or how it looked like in IDA, it's basically you had like some kind of like the flattened architecture. But because the jump and call addresses were obfuscated, there were no connections between basic blocks. So there were some connections from dispatcher to the original basic blocks because that's what the control flow flattener put there, and they didn't really care about whether you recover the connection. But like at the end of each original basic block, there was a jump, but the address was obfuscated, so IDA couldn't tell where it should go to. So it was just hanging there. And then because of that, I have a bunch of basic blocks which were just like floating around like clouds without connection to any other basic blocks. So in that case, that's also why it didn't make sense, or it was very difficult to do any kind of programmatic recovery because even if I deal with the control flow flattening, I still had to, like I used emulation to recover the jump addresses and the call addresses. With that, at least I know which other functions are called. But then making this work together with the control for deflattening, let's call it this way, that was just so too much pain. So I think adding multiple layers of obfuscation on top of that, that's so far that's the most pain I had. Yeah.
Thanks.
Sure. All right. If there are no questions, then thanks. Oh, there is one. Yeah. Sorry.
I would like to ask you if you ever seen this flattening technique applied to an interpreted language like JavaScript.
Not with JavaScript, but I would guess that there is something for JavaScript. So there is different tools for .NET, for C, C++. I've seen many obfuscations for JavaScript. And since, for instance, as I showed you, Tigress is also source code level, so that would similarly apply to, JavaScript as well. So what I'm saying is that you could implement the same techniques on the JavaScript source code. Whether there are existing tools, I don't know. It's worth the Googling.
Okay, thank you.
Sure.
Any other question? Okay, so thank you, Geri, and thank you for the presentation. We can give him again another round of applause.
Thanks.